Okay, now in this part we are going to talk about the casting processes, and once again this is not going to be a detailed one. We are only going to go through these processes officially, so we can talk about it further in the class. So we mentioned earlier that the casting processes simply can have two categorizations, which are the first one, expandable mold casting, and also we can have the permanent mold casting. From the name expandable, that the mold is going to be sacrificed after the casting process, and for the permanent we can use the same mold for multiple times. So expandable mold casting, and in this case the mold is going to be destroyed to remove the casting, as we mentioned earlier. So each time we would like to make the part, we should have a new mold. An example for that are the sand casting, the shell casting, the investment casting, and the last form casting. And also we can use the plaster mold and the ceramic mold casting. The disadvantage is that we're going to get more complex shape can be done with the expandable mold casting. What disadvantage is the production rate is going to be often limited by the time to make the mold rather than the casting itself. The permanent mold casting processes is going to be in contrary to the sand casting. This permanent mold casting, the mold is going to be used to produce not single but mainly many casting parts. Example is going to be the basic mold casting. We can have the die casting and we can have the centrifugal casting. Disadvantage are the higher production rate, but disadvantage is less complicated geometries can be done. Sand casting is the most widely used of the casting processes, and nearly all the alloys can be have a sand casting, whatever the temperature of the melting is going to be. Now this is one of the main advantages of the sand casting, because the mold itself is made of sand, so it's going to take any temperature up to 10,000 centigrade or maybe higher. The can cast metals with a high melting temperature, such as the steel, nickel, and the titanium, which cannot be done with the other types of the casting processes. The casting range in sizes from very small to very large parts, and the production quantity can be from 1 to millions at the same process. And I would like you to remember this diagram. It's very important. What are the sand casting processes steps? So take a look for this one. First you have to make the core if it's needed, and you are going to insert it in the pattern making, mold making. The mold is going to be made after preparation of the sand to build the mold, and then we have to after finishing the mold we are going to prepare the raw metal, do the melting process, do the pouring, wait for the solidification and cooling process to occur, remove all the sand, cleaning and the inspection, and we're going to have the finished casting. So these are the processes by photos. We are going to describe that in the class, how to start with preparing all the metals. We have you remember the box, which is the flask. We are going to take the upper side and the lower side. The parting line is going to be in the middle. It should be separated by using the talc powder, for example. And then simply we're going to do the flask filled with the metal after removing the pattern. Wait for the solidification to occur. We're going to have the finished part. After do some simple machining for it, we're going to have the final part to be ready. Okay, so that's how the pouring of the metal we have. We always going to have an escape for the gases we are going to generate through the pouring process. So that's what will happen. We pour the metal, and it's going to start to fill the cavity, losing the temperature at the same time, and the solidification will simply happening. Now these is small tubes. Actually, as we mentioned earlier, is going to be the razors, and also is going to provide an escape for the gases and the unwanted material, the excessive material. So this is an example of the sand casting processes for different shapes. Now this one, the one to the left, show you obviously the pouring cup, the upright flask, and we have the razor and the finished part through the runner parts. Now the patterns in the sand casting are used to form the mold cavity, and it's a full size of the model of the original part with little bit oversized. So the pattern can be either a solid pattern or the split patterns, or it can be the match plate pattern, and it can be the cop and drag pattern. Okay, I'll go through this one. The core, which usually again to made of the sand, is served to produce the internal cavities and holes in the casting. In some cases, they have to be supported by the chaplets, which this nail thing and the figure B, as obviously you can see on the right diagram here. So the chaplets are usually made of the plastic and it's going to be melted and it's going to be part of the casted part, keeping the core hanging on the arm. This is how we make the core in the foundry. We have the core box. It's going to be filled with the sand and it should be cooked to have the strength required to be held. The foundry sand, which usually again to made of the silica or the silica mixed with other minerals, but as you know that the silica is not going to be self-holding material. So but it have good refractory properties for the high temperature. The smaller grain size for better surface finishing on the part. The large grain size is going to be more permeable, so that means it's going to allowing all the gases to escape during the pouring process, but it's going to have bad surface finishing. Irregular grain shapes are going to strengthen the mold due to the interlocking process compared to the rounded grains. Now just remember that you have a box you are going to fill with the spherical marble. So they're not going to hold each other as in the case if you're going to have a box filled with the irregular shape particles, because in this case we are going to have what we call the interlock processes, that each particle is going to hold each other, so they're not going to have the flowing process. But the problem with the irregular grains is that we're going to have the reducing of the permeability, and this is simply going to increase the cooling time for the part. We need to use the binders to keep the foundry sand particles together, and usually the sand is going to be a mixture of the fresh and recycled sand, which is going to contain 90% of the silica, 3% of the water, and 7% of the clay. Now when we mention the clay, actually the clay is going to be the binder material. The grain size and the grain shape are very important as they are going to define the surface quality of the casting and the major mold parameters such as the strength and the permeability. The type of the sand mold is going to be either the green sand mold. The green means is going to contain moisture at the time of the pouring. We can have the dry sand mold. That means it's going to remove all the moisture out of it. So we are going to use, in this case, the clay. You must have the moisture. So simply, if I'm going to use an organic binders, it's going to improve the strength of the mold and it's going to remove the moisture out of it. We can have the skin dried mold, which is going to be usually a drying mold cavity surface of the green sand, which is going to have the depth of 10 to 25 millimeter. Simply we can do that by exposing the mold to a torch or the heating lamps. This will be the process of mixing the sand with the clay with the other material by using the blow plates to move the sand and the Mueller wheels to mix the components together. The mold making is, we have three methods to do the mold making. Either is going to be by using the hand packing, or we can use the machine packing for bigger parts, or we can use the automated methods for the higher production rate. The desirable mold properties are: first, it should have a good strength. Second, it should have a good permeability. Third, good thermal stability and resistant to the collapsibility. And the fifth point is going to be the reusability, so we can use the sand after the next process. The second type of the sand casting is called the vacuum molding. In the vacuum molding is an advanced sand casting process. So instead of using the clay or the binders, we can simply compact the sand by using the vacuum effect. Okay, so this will be putting the film heater, start to do the vacuum, fill with the sand, and the sand is going to be compacted over the part pattern, remove the pattern, and we're going to have the cavity inside. Fill the cavity, we're going to have the cassette part, remove the flask, and we're going to have the cassette part to occur. Now we're using the vacuum, and this is the main disadvantage for this process. So the vacuum process pressure is going to effect is going to be added to make the sand mold rather than using the chemical binders. Then the whole sand can be simply reused for the next step. The advantage is we're going to have an easy recovery of the sand since we're going to have no binders, and also the sand does not require a mechanical reconditioning done when the binders are going to be used, and since no water is going to be mixed with the sand, the moisture related defects are going to be avoided. But the disadvantage is that the time required to do the vacuuming process is going to be a negative effect, because we're going to have a slow process to be completed. And also no readily adoption for the mechanizations in this process occurred. The other process we can have for the expandable molding is what we call the shell molding. So also known as a DBM process. DBM in the ceramic shell molding process, and because the mold is going to have a thin wall shell of the ceramic or sand, it's called the shell mold. Since the solid naphthalene is going to be used for preparing the molds, a complicated shapes and thin casting can simply be produced with this process. So what's happened first, we're going to have the heated pattern, and we have in the box a sand with a resin binder, which is ceramic, of course. Okay, this is done box. If I'm going to flip the box, you can see that the sand with the resin binder is going to build up on the pattern shape. If I'm going to flip it back, I'm going to have a shell created on the surface of the pattern. Now simply I can heat up the shell to give it more strengthability. Remove the shell, put two shells together to generate the cavity of the pattern required within the flask, supported by the metal shots just to have the holding parts. And simply I'm going to fill the shell cavities with the molten metal, and this will generate the parts required by the casting process. This is another example of the these are an example of using the shell casting, and for example this one is for making the cylindrical for the marine engine. So this is foundry for the shell casting, and advantages are, now the main advantage is we are going to have a good surface finish with up to 2.5 millimeter. Also we have a good dimensional accuracy by plus minus 2.5 millimeter difference. It's suitable for the mass production because we just can do the manufacturing of the shells by a high rate. The disadvantages are the expensive metal pattern, as the one you can see on your right side. And the area of the applications are the mass of the steel casting of less than 10 kilograms. The loss form is also known as the loss pattern process. We are going to use the evaporative foam process, where the full mold process and expandable polyester processes. The mold is going to be made from the sand packed around the pattern, which is made of the polystyrene foam. So this is the only process we're now going to move the pattern. Now, as you can see in the photo number 1, we are going to make the pattern out of foam. We have to separate with the refractory compound just to give it some strength and have good surface finishing. Then we are going to pack it inside the flask with the sand packed around the pattern to support the pattern, the metal after the evaporation of the pattern. As we are going to add the molten metal, it's going to evaporate the pattern and take its place, and at the end we are going to finish with the cassette part ready to be used. This is an example of the foam pattern, okay, and the cassette part. Now you can see a small engine block can be done by the foam, expandable foam casting. The the valve shell, different types of pulleys, and other different parts which have a quite complicated shape. You can notice from this one that the quality of the casting also is going to be good, and this mainly is going to be related to the spraying of the refractory compound around the foam pattern. Okay, now this is the massive production of the foam patterns for making different parts. The advantage of this process is that the pattern need to be removed. No need to be removed from the mold, and it's going to simplify and the speed of the mold making, because we are going to have two mold halves are not going to be required as in the case of the conventional green sand mold. But the disadvantage is that we need a new pattern is going to be needed for every casting, and the economic justification of the process is going to be highly dependent on the cost of the producing of the patterns. The applications are for the production of the casting for the automobile engine. The automated and the integrated manufacturing systems are going to be used to first mold the polystyrene foam pattern, and then we have to feed them into the downstream casting operation. The investment casting was something similar to the evaporative foam casting, but in this case we are going to use the wax instead of the foam. So let's see how this process is going to happen. In the investment casting, the pattern is going to be made of wax, which is going to be melted after making the mold to produce the mold cavity. So we're not going to leave the pattern inside, we're going to melt it and reuse the wax once again. So this is one of the process. I'm going to make the pattern, I'm going to put it fixed on the wax spur, and then I'm going to dip it in the, for example, the ceramic material, leave it to solidify, having the shell, heat it up. I'm going to get rid of the wax inside, fill with the molten metal, and after the classification I can remove the shell and get the cassette part. Now these are also some of the steps we're going to do for the wax pattern, and then we're going to simply using the ceramic slurry to dip it in, and then I'm going to remove the molten wax by heating, fill it with the molten metal, and then we can simply remove the shell to get the finished part. We are going to have in this case a small in size complex parts such as the art pieces, the jewelry, the dental fixtures, from all types of the metals. Used to produce a machine element such as the gas turbine plate, which is going to have a very complicated shape and very good surface finishing, the pinion gears and extra, which does not require or required only little subsequent machining after the formation process. Okay, now this is once again more folders for that. Advantage are the part is going to have a great complexibility and intensity can be cast. Close dimensional control and good surface finishing. The wax can be usually be recovered for the reuse, and this is a net shape process, so no additional machining is going to be normally required. Disadvantage is that many process steps are required, and relatively is going to be expensive process, especially because the making of the wax patterns. The other process is using the plaster mold casting. Similar to the sand casting, except that instead of the sand, we are going to use the plaster of Paris, which is the gypsum. In the mold making, the plaster and the water mixture is going to be poured over the plastic or the metal pattern, and it's going to be allowed to set. The wood pattern is not generally used due to the extended contact with the water is going to damage the pattern. The plaster mixture is going to readily flow around the pattern and it's going to capture its fine details and the good surface finishing. And the advantage of this process is we're going to have good accuracy and surface finishing, and we're going to have the capability of making thin cross sections. Disadvantage is that the mold must be break to remove the moisture, and the moisture can cause a problem in the casting. And the mold strength is lost if over baked, and the plaster mold cannot stand at the high temperature, and this is limited to lower melting point alloys only. The ceramic mold casting is similar to the previous process, but the mold is going to be made of refractory ceramic material that can withstand a higher temperature than the plaster. It can be used to cast steel, cast iron, and other high temperature alloys. The application is similar to those for the plaster mold casting, except for the metal's height cast. Advantage is we are going to have a good accuracy, and surface finishing are also going to be similar. Now the other type is going to be covered in the last section of this lecture, is going to be the permanent mold casting.